Okay, so moving away from 3D models, I'll give you an overview of uncertainty in geological maps. So to start off with, we'll have a look at what a map is. So really, it's a topological representation of lithology interactions, so including structures. It's essentially a 2D model, and we create it through interpolating between observations, which could be compared to how implicit or even explicit models are made. So rather than looking at the variation in how, if we change the observations, the implicit model will produce a model, we're going to look at how 40 students will produce maps of the same area differently. So I'm using variability between the maps as a proxy for uncertainty. I'm starting off with 40 maps of the LD structure at Broken Hill, so it's a relatively complex area. There's 5 different lithologies the students are mapping, and there's 5 structural events that they're mainly looking at. And what I aim to do is locate and quantify variability between the maps, and also using what Tom was talking about before, the geodiversity metrics. I'm going to compare how they vary, and hopefully we'll be able to classify some of the maps into different groups or species. So Tom gave you a quick overview of the uncertainty types. I won't go through it just to save time, but there's a diagram which is a little bit different. So this is an example map of the LD structure. It is just one of the maps, so it's not the right map. And there's the lithologies which the students map. So there's the class-bearing biotite gneiss, which I'll abbreviate as CBBG, the interbedded P-Latin samopelitic schist, which is the IPP, and then there's the pegmatite, which I have as the PEG. The felsic gneiss is FELS, and then the amphibolite is AMPH. So in the diagrams, I'll make it a bit easier for you. So there's just a blow-up of where we're seeing the felsic gneiss and the amphibolite intrusives. They're obviously a lot smaller than the other lithologies the students were mapping. So visualizing variability, I'm going to use 2 different techniques. Both of them have been used in 3D. So Mark used stratigraphic variability and Florian Wellman used information entropy. They do show you different things. So stratigraphic variability will look at how different the group of maps are, or how likely the mode model is. So the most common lithology at that location, how often is, or how many maps actually have that. Whereas information entropy will show you how many different lithologies can occur at the one location. And so when we have a look at the previous map, which was with the small intrusive, so the amphibolite and the felsic gneiss, they're sort of a little bit random in where they're occurring, so they might occur more in the information entropy. So here's just a diagram showing you the differences, and you can see this example, there's the 3 lithologies occurring, and then this one, there's 5, so we've got the same stratigraphic variability but different information entropy values. So here's the stratigraphic variability map of the LD structure. You can see that there are some clear high areas, so you can see an outline of the contact between what you'd assume would be the class-bearing biotite gneiss in the centre, and then the layers which are repeated throughout. But on the western limb, you don't see as clear a structure as over here. And that is possibly due to how complex that area is, or it's just that students aren't going there. But it's something to sort of keep in mind when I show you some of the later images. And obviously, down here, we are seeing quite a high area of variability, so it is the furthest away from where the students go into the field, so they're possibly not going there, and it's just guessing. And there's a confidence map which shows you the mode lithology, but only when it's in 70% of the map. So you can see that the main contacts that I show in the stratigraphic variability, you can see them, and in the western limb, you don't see all that much occurring. And obviously down here, there's a little bit of the interbedded, but it's only in the 2012 maps. And so I'll move on to the information entropy. Now, you can see a similar outline of the structure, which is sort of what you would expect, but a few different areas pop out as being high. So this western limb here is significantly higher than what we were seeing, so there are clear bands, and that could be that there is a contact that's being mapped, but maybe the students aren't actually mapping the same lithology in that location. So they can see there's a difference in the lithology, but they're not actually identifying it correctly. Or maybe the felsic gneiss and the amphibolite are contributing a little bit more to that. And you can see there's a few areas that when you compare the 2011 to the 2012 are a little bit different. So that probably suggests that maybe the students in 2011 weren't concentrating in different areas, or they weren't mapping as much of the felsic gneiss. Maybe the demonstrators who were running the students through how to map in specific areas, such as up here, showed them different things, and which is sort of what we would expect to see. So, showing you a map of where the felsic gneiss occurs. So this basically shows the probability of finding it out of the 40 maps, and I think at the highest point it's about 25%. So it's not really mapped in the same location that often. Whereas the amphibolite is mapped in two places quite consistently, but they're actually seen on the Google Earth image, so everybody is interpreting them off that, most likely. And then this area here was where the students go at the start of the trip, which means that it's an outcrop that if they're with one of the lecturers, they'll probably see it. And then the rest of it, you see clear bands of sort of where it's occurring, but you don't see it occurring in the one location across all of the maps. So I've gone through where the variability is, but it doesn't really show you how each map differs. And building on the sort of geodiversity stuff that Mark and Tom have been doing, it's kind of interesting to see how students are mapping. So it's something to do with style that is contributing to the variability between them, or is it just that they're mapping randomly, which could be. So biodiversity basically is a measure of how, or showing how different species vary at a specific location. So Mark brought in or introduced it for looking at geological models, and what we're trying to do is say that if we've got a set of models, there's a group that have these characteristics, a group that have these characteristics, and what's similar between them. So Mark used principal component analysis. I won't go into too much detail about what it is, but I've actually chosen to use self-organising maps, which is what Tom showed you before, for a couple of reasons. They handle data sets that aren't normally distributed better, so if they're sort of a bit random, and also allow for more metrics to be used. With the principal component analysis, it doesn't work as well if you've got, say, 10 metrics for 5 lithologies, then you're going to have to cut them down. So what Mark did was did one principal component analysis for each lithology, and then chose the ones which showed the most variability. Self-organising maps allows you to use more. And what it will do is categorise the maps into groups that are similar. So it's a dimension reduction tool. So I'll give you a quick example of using SOMs. This is just a data set that I've got off Stephen Fraser, which he uses in some presentations. And it just shows some characteristics of animals. And so this is a SOMs map. Each one of these hexagons is a node, and that represents a value for each of the metrics. So in this case, whether they've got feathers, hair, hooves, etc. So a red value means that those nodes have a high for that. Blue will represent low. So you can see that something that's got feathers is probably going to be smaller. It probably doesn't have legs. It may not be big. etc. So it sort of shows what characteristics fall together. And then from that we can cluster it, which shows you which animals are grouped together. And depending on how many clusters you have is sort of the resolution of how well they're grouped. So moving on to the geodiversity metrics. The metrics that I've chosen to use for the maps are the aspect ratio, and so that is the major axis divided by the minor axis, and that's only for the amphibolite and the felsic gneiss, mainly because the interbedded and the class-bearing biotite gneiss don't really form shapes that are particularly good to analyse with this technique, so I decided not to use it. There's also the orientation, which I've also used on those two lithologies, which is just how much how far they've rotated from horizontal. Then there's the surface area. So what I've done is calculate the maximum surface area for a specific lithology, and there's also the number of units and the total surface area. So it can give you an idea of what style of mapping the students are doing. There's also the contact relationship, so the total distance of contact between specific lithologies, which is interesting to look at because you may not expect to see some lithologies within other ones, so having a contact of that suggests that it could be an outlier. There's the geological complexity, which is the short distance. So for example, at this location here, the complexity would be 2 because there's the lithology of that cell and then the other lithology around it, whereas in here it will be 1 and here it will be 3. So there's the component maps for the self-organizing maps. I won't go through all of them because there's too many, but I've brought out a couple of interesting ones to look at, which is the number of regions for the pegmatite. So the pegmatite is mapped quite differently, and I'll show you some pictures soon that will sort of show a bit more. But remember that it's in that top left-hand corner. There's a number of regions for the felsic gneiss. So that's important because it shows how often the students are actually recording the felsic gneiss. So if they only record it once, then they're possibly not seeing it where it should be occurring. There's the contact between the interbedded and the felsic gneiss, which correlates well, so you should sort of expect the felsic gneiss to be within the interbedded. Then there's the maximum surface area for the pegmatite, and you can see that it mainly is falling in the area where the other metrics aren't representing. So suggests that a lot of the maps are actually classified by how large the surface area of the pegmatite is, so how much of the pegmatite's being mapped, and then there's the number of regions for the interbedded, which is similar to the number of regions for the pegmatite, and that could be because of the contact between them. So what I've done is I've clustered the self-organising map that you see before. I've only used 3 clusters because I could have used 10, but having only 40 maps, it's better to have a coarser resolution and actually see some groups of the maps, even though they're probably not grouped as well. The Umatrix is a representation of how far apart each node is. So the black dots represent where a map is. The size of the dot represents how many maps are sort of classified by that node. And you can see that in this corner, the maps are probably further apart than the ones down here. So all of the maps around here with the blue, the Umatrix is showing that the nodes aren't that far apart. So looking at the groups, so we've got group 1, 2 and 3. Now you can look at group 1 here, and that, or species 1, that shows you quite sort of the outlier maps, I guess. These ones are sort of probably the more basic representation of what you'd expect. So they're more similar to the mode confidence map that I showed you before. And then these ones here have more of the felsic gneiss. They seem to be a little bit more detailed, but given the cell size I've used of 5 metres, you sort of can't judge that well. So I'll show you the mode map again, and if we go back to the species, I think that it looks very similar to species 2. So species 2 was this one here, which is classifying most of the maps. So that's what you'd expect, that the majority of the maps are contributing to the mode. And from this, you can say that there is a lot of variability in how students are mapping or mapping geology. And you can say that students can't map, which could be true, but there's no reason to say that anybody else is able to map any better, and that variability that we see students doing isn't going to be the same or similar. So it's something to consider. The felsic gneiss and the amphibolite were rarely mapped consistently in the one location. So that's something to think about when you're looking at a map that you don't know how good the quality of it is. Look at sort of the style of lithology, and should you expect that it is mapped in the right location. And we did see 3 clusters, and you could probably say that there's the lumpers, the blobbers and the outliers. So it's something to do with the style. And I think that self-organising maps are cool to use for geodiversity, so it should be used for more geodiversity analysis in the future.